Okay, imagine for a second that you're driving your car down the highway. You hit the gas. You're going really, really fast. Now, according to the absolute bedrock laws of physics special relativity, your car isn't just moving. It's
Mm.
physically changing shape.
Mm.
It's getting shorter. The atoms are literally crunching together in the direction you're traveling.
Yeah, that is the textbook reality. It's a phenomenon called Lorentz contraction.
Right.
We pretty much accept it because, well, the math works and it keeps the speed of light constant for everyone.
Right. But what if that whole idea, the idea that the universe physically squashes things just because they're moving,
Yeah.
what if that's a total
Well,
fantasy?
that's a very bold question to
How if
ask.
that shrinking is actually just a cover-up? A mathematical Band-Aid we slapped on a century ago because we forgot how to measure memory.
And that is the provocative thesis of the stack we're diving into today. It's this really fascinating collection of technical dialogues, some geometric proofs, and this is the part I love, a script for a Blender 3D simulation. And they all argue that we've been looking at the speed of light, well, completely backwards.
So we aren't just reading papers today, we're sort of debugging the code of reality itself.
That's a great way to put it, yeah. The source material presents a model where objects don't actually shrink when they move. And instead, it suggests that we're viewing them through a distorted lens. We're seeing a ghost of the object, and we're mistaking that ghost for the physical thing.
This is going to be a bit of a mind bender. We're about to explore a model where the speed of light reveals this gap between where we think an object is and where the light actually hits it. It challenges Einstein, it challenges our perception of now, and it uses 3D modeling to prove it. So grab your coffee because we are diving deep into the geometry of reality.
All right, let's ground this. We have to start with the setup that caused all this trouble in the first place. The source material uses a classic physics scenario, the Michelson interferometer.
Right, for anyone who, skipped that day in physics class,
Mm-hmm.
this is the device that was supposed to measure the ether back in the late 1800s. It's basically just a light splitter.
Exactly.
You shoot a beam of light, you split it in two, send them down these perpendicular arms like an L shape, bounce them off mirrors, and then bring them back together.
Precisely. In the sources model, we're asked to picture this device as a disk. Let's say it has a radius of 10 units. And this disk isn't sitting still. It's tearing through space at 10% the speed of light. That's 0.1 c.
Which is just incredibly fast. That's, what, 30,000 kilometers a second?
It is. So we've got this disk, radius 10, moving at 10% light speed. We take a snapshot at time equals 0. Now, under standard Einsteinian physics, looking at this from the outside, what happens to the arm of the device that's pointing forward? The one moving in the direction of travel?
Well, according to special relativity, it shrinks. To a stationary observer, that 10-unit arm, it physically squashes down to about 9.95 units.
Right.
I want to pause on that for a second. Why? Why does the universe demand that a piece of metal gets shorter just because it's moving?
It's a requirement. It's the only way to keep the speed of light constant for everyone. If the arm didn't get shorter, the math it breaks. See, the light traveling down that forward arm has to chase a mirror that's running away from it.
Okay.
And it bounces back. That whole trip takes a certain amount of time.
And the other arm, the one going sideways.
The light just goes up and down, basically. Yeah. It's a shorter trip overall. But the experiment, the actual Michelson-Morley experiment, showed that the light beams return at the exact same time.
So wait, you have a long trip and a shorter trip, but they finish together, like a race.
Exactly. And the only way standard physics can explain that is to say, well, the long path must have physically gotten shorter. The arm shrank. That's the only way you can balance the equation if you assume the speed of light is the same for everyone.
But this is where our source just throws a massive wrench in the gears. The observer, who is on the disk, let's say it's me, I'm sitting on this machine, I'm looking at this metal arm. It's rigid, it's steel. I know for a fact it's 10 units long. It hasn't been crushed. It's just moving.
And the source calls this the rigid body premise. The argument is, physically, locally, the arm is 10. It hasn't changed. The atoms are stable. So if the arm didn't physically shrink, how on earth do we reconcile the math? How does the light arrive on time?
This is where we leave the textbook and we enter what they call complex spacetime. The source introduces a new way of mapping the world that I honestly found really refreshing.
Yeah.
It stops treating time like some magical thing and starts treating it like information.
It does. Usually we graph things with space on the x-axis and time on the y-axis, but the source argues that this mixes up two different things. It introduces a new axis. They call it M.
M for memory.
Memory, or retardation, or information depth. Think of it as the lag that's just inherent in the universe.
The source uses a great analogy here to explain why we would even need this memory axis. The sun.
It's the perfect example, yeah. When you look up at the sun right now, let's just say at time equals 0, you aren't seeing the sun as it exists right now.
Right. I'm seeing the sun as it was 8 minutes ago.
Exactly. The light took 8 minutes to get here. So the visual sun is in your sky, but the real sun, the physical ball of gas, is actually somewhere else in its orbit because it's kept moving for those 8 minutes.
So there are two suns, the image sun that I see and the real sun that I can't see yet.
And the source argues that standard physics makes a huge mistake when it tries to smash the image and the object into the same coordinate. In this complex space-time model, the real sun is at one coordinate in space, but the image sun is deep down that m-axis, the memory axis, because of that delay.
So m is basically just a measure of how old is this picture I'm looking at.
Precisely. It's the distance into the past.
Okay, so let's apply this memory axis to our moving disk. We have the interferometer moving at 10% light speed. The source describes the shape of this device in the new space-time, not as a flat disk, but as a tent. Can you walk me through that?
A tent is a perfect way to picture it. So imagine the m-axis as the vertical pole of the tent. If the device is stationary, the delay for light to go out and come back is the same in all directions.
Okay, symmetrical.
Right. It takes the same amount of time to hit the front mirror, the back mirror, the side mirrors. So the depth in memory is equal. It's a symmetrical upright tent.
But when it starts moving?
The tent gets lopsided. Think about the mirror at the front of the disk. It's moving away from the center.
So the light has to chase it down.
Exactly. It has to travel farther. It takes longer to catch that front mirror. And that means the information coming from that mirror is older. It's deeper in the past on that m-axis. The tent pole dips way, way down.
And the mirror at the back.
You're moving towards the light from that one, so the light catches it really quickly. That information is fresher. It's very shallow on the m-axis.
So we get this lopsided shape in 4D space. The front is deep in the past. The back is close to the present. The source actually crunches the numbers on this. And I want to go over them because they're so specific.
Yeah.
It claims this explains the shrinkage without actually shrinking a thing.
Let's get into the math.
Okay, so the rigid physical location of the mirror. It's still at 10. It hasn't shrunk.
Correct. That's what they call the real object.
But the future mirror, the point where the light will actually hit it because it's running away, is at a distance of 11.11.
And that 11.11, that represents the informational load. You have to pay more distance to catch a running target.
And the past mirror, where the light seems to come from when it returns, appears at 9.99.
Because it was running towards the light source on the return trip, so that part of the trip was shorter.
So we have 11.1 and 9.09. These are the real distances the light traveled. And here's the kicker, the source points out. If you look at the shadow, these points cast onto our normal math.
You get approximately 9.95.
Boom. There it is, the Lorentz contraction number.
And this is the core argument. The source claims that the shrinkage to 9.95 isn't a physical compression of metal. It's an informational slope. It's just a compromise number that you get from the fact that light had to travel 11.11 units out and 9.09 units back.
So we're mistaking a long trip and a short trip for one single shrunken trip.
That's a very elegant way to put it. We're projecting a 4D complex reality where information delay is a real dimension onto our 3D world, and the result is this phantom shrinkage. The metal didn't change at all, the path of the light changed.
And this is where the source material gets so cool. They didn't just write down equations, they included a Python script for Blender. For anyone who doesn't know, Blender is 3D modeling software. They actually coded a simulation to visualize this lie.
It's a brilliant move, really. It takes the debate from abstract algebra to something you can actually see. The script plots these points we just talked about. It uses red for space, blue for time, and green for this new memory axis.
And there's this specific object in the simulation they call the white sphere. I found this kind of haunting, actually.
The white sphere represents the fantasy. It's placed exactly at 10 units, moving along with the observer. It's where our intuition says, the mirror is right there, it's attached to the arm, it's solid.
It's the rigid body, it's what I think I'm seeing.
Right, but then the simulation plots the yellow line, which is the actual path of the light, and this is the visual aha moment. The yellow line completely misses the white sphere.
It misses it.
Never touches it. The light shoots past the white sphere to hit the future mirror at that 11.11 mark, the red point, and then it returns from the past mirror, the green point.
So the object we think we are measuring, the white sphere, is just stranded.
The source calls it an island of information. Light never will tact with it. It's a ghost. We're assuming the mirror is at position 10 at time 0, but light can never interact with position 10 at time 0 because of the travel time. We are chasing a ghost, and the math of relativity, according to this source, is just us trying to describe the behavior of that ghost.
That's unsettling. It really makes you question what now even means. If I can't touch now with light, does it even exist for me?
That's the philosophical depth of this model, isn't it? Now is a local construct. Interaction requires a delay. You can never touch the present moment of something distant. You can only touch its past or its future.
To explain this delay, the source brings up a classic analogy that I think needs a bit of a fix. The lake and the boat, we've all heard this one, a boat moving through water, making ripples.
Yes, but usually people say, imagine a boat moving at 10% light speed and emitting sound waves. But the source points out that this analogy totally fails if you use sound.
Because sound is so slow.
Exactly. If a boat is moving at 0.1 c, that's 30,000 kilometers per second, and it emits a sound wave moving at 300 meters per second, the sound will never, ever catch the boat.
Right. The boat leaves the sound in the dust. It's like trying to catch a fighter jet with a turtle.
So the analogy only works if the ripples are also moving at light speed.
Okay.
We have to assume the ripples are light, so they move at c. So now imagine the boat is the mirror, moving at 0.1 c, and the ripple is light, moving at c.
Okay, so I've got a sideways boat, that's the arm going up and down, and a forward boat, the arm moving forward.
The sideways boat is relatively easy for the ripple to catch. It just has to angle itself a bit. It's a diagonal path. But the forward boat is running away. The ripple has to travel that huge distance, the 11.11 units we talked about, just to catch up to it.
And the ripple has to come back.
And standard physics, the Michelson-Morley result, says both ripples return to the start at the exact same time.
Which seems impossible, if one had to run a marathon and the other just went for a quick jog.
It is impossible unless...
Unless the marathon was actually a jog.
Exactly. The source argues that standard physics says the only way they can arrive simultaneously is if the forward distance magically shortened. It forces the marathon to become a jog by shrinking the road.
And the source says?
The source says, no, the distances are real. 11.1 is real. 9.9 is real. The simultaneous arrival isn't due to the compression of the boat. It's due to the geometry of the information flow.
It feels like we're solving a crime here. We have the body, the light returning at the same time, and we have two suspects. Suspect A is space shrinking. Suspect B is information delay.
And for 100 years, suspect A has been the one convicted. This source is trying to file for an appeal.
Speaking of crimes, the source has this section titled The King Killer. That sounds incredibly dramatic for a physics paper. Who is the king?
The king refers to the established lineage of physics. Newton, Maxwell, and specifically a man named James Bradley.
I feel like Bradley doesn't get enough credit in the history books. What did he do?
He discovered aberration back in the 1700s. It's a phenomenon that's easiest to explain with rain and umbrellas. Imagine you're standing still in the rain, you hold your umbrella straight up.
Simple enough.
Now you start running. If you keep the umbrella straight up, your front gets all wet, you're running into the falling drops. So what do?
I tilt the umbrella forward. Into the rain.
Exactly. That tilt is aberration. And Bradley noticed you have to do the same thing with telescopes. Since the Earth is moving, you have to tilt your telescope slightly to catch the light from a star. It was actually one of the first solid proofs that the Earth moves.
So the tilt is proof of motion. If you're moving through a field of light, you have to tilt.
Correct. Now, here's the accusation. The source argues that Einstein basically ignored this tilt when he came up with his famous train thought experiment.
The light clock on the train. I mean, this is the cornerstone of relativity.
It is, Einstein says. Imagine you're on a moving train. You shine a light at the ceiling. To you, the passenger on the train, the light goes straight up and straight down, vertical.
That seems reasonable. If I toss a ball up on a train, it comes right back to my hand.
But the source says, no, that violates Bradley's discovery. Just as Bradley had to tilt the telescope, the light inside the moving train should be affected by the train's motion through the electromagnetic field. The source claims the light should actually appear to move diagonally or tilt even for the passenger.
Wait, so the source is saying Einstein just forced the light to go straight up?
That's the king killer moment. The source claims Einstein killed the king. He killed the physical reality of aberration by insisting that the passenger's view must be vertical.
And by insisting it's vertical.
He broke the geometry. Think about it. If the light goes straight up for the passenger, but it goes diagonally for the person on the platform outside, you have a mismatch. The diagonal path is longer.
Right, the hypotenuse of a triangle.
So if the speed of light must be constant for both people, but one path is longer than the other, the only way to make the math balance is to say that time itself slowed down for the passenger.
So, the source is suggesting that time dilation and length contraction are basically just cover-ups.
Cover-ups for the fact that we forgot to tilt the umbrella. The source argues that if we properly accounted for the tilt of aberration and the informational delay of the m-axis, we wouldn't need to shrink space or slow time. We'd just see a complex 4D geometry where information takes different paths.
That is such a heavy claim.
Yeah.
It's basically saying special relativity is a mathematical fix for a geometric oversight. It's like finding out your house isn't haunted, the floor is just crooked.
It is a massive claim. And to be fair, standard physics has a century of experimental verification. I mean, GPS satellites, particle accelerators, they all rely on relativity math working. But what's compelling about this source is the internal logic. It asks us to prioritize the rigid body, the physical reality of the object, over the constant view of the observer.
It brings us right back to that white sphere in the Blender simulation. The rigid body is there. It exists. It's real. But we can't see it directly. We only see the light that missed it.
We are measuring the echoes. That's it.
So let's just unpack where we've been. We started with a metal arm that physics says has to shrink. We moved to a complex space-time, where that shrinkage is revealed to be a shadow of a future and past position, the 11.11 and the 9.09.
We visualized it with a computer simulation showing light actually missing its physical target, creating that island of information. And we ended up in the 18th century wondering if Einstein ignored the lesson of the umbrella in the rain.
It's amazing how looking at the same problem, the speed of light, from a slightly different angle, literally a different axis, just it changes everything. It changes the universe from a place that squashes matter to a place that delays information.
It really highlights the difference between measurement and reality. Just because we measure a shrinkage doesn't mean the metal actually crunched. It might just mean our ruler is made of light, and light takes time to travel.
That's the takeaway for me. We're measuring the world with a ruler that bends and stretches based on how fast we're moving.
And this source suggests we can mathematically straighten that ruler out if we just acknowledge the memory axis.
Before we wrap up, I want to leave you with something to chew on. You mentioned that now is a local construct. But looking at this source material, it feels a bit more existential than that.
It raises a pretty profound question. If what we call now-yay is just a thin slice of a massive, complex pipe of memory and information, are we ever actually seeing the world as it truly is? Or are we just living in a delayed shadow that our brains sort of force into a familiar shape?
Are we interacting with reality or just the receipt that reality printed out milliseconds ago?
It's a disturbing but also a beautiful thought. We might be living in the wake of the universe, not at its bow.
Thank you for taking this deep dive with us. We hope you look at the stars and maybe your own speedometer a little differently from now on.
Keep questioning the constants.
See you next time.